Ma'am,
Yeah.
ma'am, like before the call was cut, ma'am, we were discussing about Intel's monopoly and all. Ma'am, now with AMD pretty much dominating everywhere, ma'am, do you think
AMD is
there's gonna be
dominating.
almost everywhere, ma'am? Like in the server lineups, the Epic solutions seem to be better, and in their desktop replacements, Ryzen has been proven to be much better with a higher core count and more performance across all cores. So, do you think it could be much better later
Yeah,
on?
the problem is AMD also, you know, all AMD processors or most of the AMD processors are Intel clones. You know, when we actually start studying the depth of the processor architectures in this class, I think I probably may not have been there, or because I didn't attend one class of Rukma's. You know, they talk about architecture consisting of instruction set architecture, the micro architecture, and one more component, right? NSC and Patterson in the first chapter. I haven't read the first chapter because I'm trying to read my chapters.
Instruction set architecture, micro architecture, and computer organization.
Yeah, so when you actually go into the details, when we go into the details of the architecture, what you'll realize is that, see, the instruction set architecture today is Intel's ISA. You know, every processor uses Intel's ISA
Is
today.
using the CISC that were like, but that's also another point. Like now, because AMD first actually came to the 64-bit, like they came ahead of Intel, and
Oh,
when
don't
Intel
talk
tried,
about AMD. If you want to talk about 64-bit, in
yes, ma'am.
93, I think, DEC
Okay.
actually invented the first 64-bit processor, which is Alpha.
Oh,
And SGI invented it in around 96, probably. And SGI actually implemented a 64-bit file system in 96, 97 timeframe. You people don't know history. We know history because we actually lived through that. If you want to know, Sun had this processor called Niagara, which in I think around 2007 or so had 16 cores. At that time, you know, Intel was just coming out with a dual processor, not dual core. Whereas Sun already had 16 cores in the Niagara processors. I mean, like the hardware manufacturer, that's what I'm saying. Hardware, if you look at it, just as Microsoft is like the worst operating system. I'm sorry, but you know, it still doesn't come up to the Unix standard. Similarly, Intel never actually reached the standard set by all those people long, long ago. So AMD, what they do, they take the this is what I know, Intel's instruction set architecture, and then their micro architecture and all are very different. Okay. So because of that, they achieve much better speeds than the Intel processors.
yes, ma'am. And also like because like what I had initially read was that AMD like like who was ahead of Intel in actually properly implementing 64-bit natively. So when Intel actually came on, the x86 64 was a rather shoddy.
Yeah, it
It just
is because the problem is the way Intel accesses the thing. So, okay, let me just maybe because we are discussing the register memory architecture. Okay. Uh, Intel actually allows you to, I mean, it has an instruction set architecture where one of the operands is a memory location. Okay. So, because if you have already seen the MIPS ISA videos that I have put up, you will notice that it very clearly says if you want to do an operation, you have to bring it from the memory into register and then only you can operate, right? But whereas Intel's ISA allows you to directly operate on a memory location in theory. But because that doesn't go well with the concept of pipelining, which we will be talking about in future, right? With assembly, pipelining is like your assembly line in the car, where different people work on different parts simultaneously to build a car much faster than if one person was sitting and doing everything sequential. Okay, so pipelining allows you to parallelize different parts of instruction execution. Now, if you want to do pipelining, it's not possible to do with memory like that. It just doesn't work well with pipelining. So what did Intel do? Intel actually built a hardware component that internally translates these memory operation ISA to load store ISA and generates more RISC-like code, which is what is actually executed. So they have an intermediate step, right, which is translation. No, so what does your compiler do? Your compiler will actually, translate your high-level language code into the instructions given by the instruction set architecture. Okay. See, you can't write some instruction which is not in your instruction set architecture, right? So compiler's job is to convert your high-level language into the instructions provided by the particular hardware. Okay, so it does that. But what does Intel do? It takes the binary code and it has a hardware component which converts it into more RISC-like code, which is then executed. So you do have some loss of performance there, however fast the hardware may be, right? So there are many such, what should I say, hacks in the hardware. And people don't like, really good hardware engineers don't like Intel processors. But Intel has become quite big, and AMD may have better processors, but unfortunately, they're all Intel clones, right? Intel is doing some things which are very, very aggressive in certain ways. Like, for example, the cryptographic standard AES, which is the encryption algorithm AES, they actually made that as a instruction in the instruction set architecture in Intel. Of course, this goes completely against the policy of NSE and Patterson. But, that allows it to be very fast when you are trying to use it for cryptographic functions. So if you have a specific, probably they implement it only in one line of processors, which may be used for networking purposes. So it's like that. Intel has gone far on certain aspects.
It's basically like just a symbol of hacks wherever to increase performance rather than addressing the base line.
Yeah. So, what happens is whether it is Intel or Microsoft, they're also stuck with one basic problem of backward compatibility, right? Because something which ran in their previous system should also run in the next generation system, and this kills half the problem, half their attempts to also innovate. Their desperate attempts to innovate are always stymied by this backward compatibility problem. So, I remember when I worked in Microsoft, I was working on Windows Vista, one of their worst operating systems. No wonder I got fed up with it. But the thing is, they thought they are building afresh, they'll not bother about backward compatibility, but they are so straight-jacketed in their thinking, they can't get out of that. So, it's pretty bad, very bad design. because of that. So, some parts will be like that. Some parts will be good innovations, but yeah, backward compatibility always is a problem. Cisco also has that problem, but Cisco actually is a very good, hardware engineering team. So it's a superb. In fact, they brought their hardware engineers from. Oh, not they. Juniper brought their hardware engineers from SGI and Sun because they were the best hardware engineers at that time. So, okay, so let's come to, I was talking about how do you interpret your addresses, right? So byte order, we have little endian, big endian. You know that, I don't have to talk about it. That's what is the byte order problem. The alignment problem, okay, which, there was a question on that. And I have actually put in a very beautiful explanation in the forum. I don't know how many of you have seen it, but basically the point is, okay, there are two terms here that I want to make clear because I have been reading, struggling. Maybe ma'am can also add more to what I say. Because there is something called byte or word addressing, and then you have alignment. So you have, how do you address a memory location and what is the alignment of the memory location? There are two aspects to which you need to keep in mind. And I thought it was in this series of videos only that I saw, but I could be wrong. So if it's not there, because I've been looking at different resources. Some I have put up, I haven't put up everything because we have also thought that we will not put up all resources that we are looking at, primarily because we didn't want you to feel overloaded, right? I mean, if we put in too many things, you don't have time to do all that. So we are filtering stuff, putting in only what we think you need, even though there are some beautiful, lectures from Carnegie Mellon University especially. So anyway, the point is that byte addressing, word addressing, what does it mean? If you say that your processor is capable of byte addressing, then you can actually put in an address which addresses every byte. So you can say byte 0, byte 1, byte 2, byte 3, and so on. So the address can be every byte in your memory. If you say word addressing, the only permissible addresses that you can put on the address bus are 0, 4, 8, 12, and so on. Okay. That's what is addressing. What about alignment? Now, there are different types of alignment. I was only familiar with word alignment before I read this book. Prior to 2014, somehow I was only more aware of word alignment. What does it mean that your address, so this is where I was confused between word addressing and word alignment. So obviously a word aligned processor will not allow you to, you know, you cannot address any particular address because your variables will not be available at those locations, right? When you're saying it's a word aligned address, it means that your variables should be located only at word boundaries. Okay. Now, a very simple experiment I would like you people to do would be define a structure, right? Define a structure in C. Have a char, integer, char, float, char, double, something like that in that order, okay? And see what's the size of the structure. Change the order of the variables, okay, and see the size of the structure. So instead of having char, int, char, float, char, double, have char, int, or char, int, char, then char, float, something like that, and see what, does it change the size of your structure? And if it changes, why does it change? This experiment will be very, very useful for you to understand whether, yeah, why does it do padding to the structure? That's the question. Where does it do padding to the structure? Why does it do padding to the structure? Can you answer that question?
So that demand when we access
Okay.
it, so in execution time, it doesn't read the other part, like doesn't read the next variable.
Yeah, like Subhash said, to fill in a word. So the point is, if you have char variable, will it fill in the word and the next char will be at the next word boundary? So what I mean to say is, supposing you have two characters in your structure, what will be the size of your structure? 4 bytes. On a 64-bit processor also. Won't it be 2 bytes? It's not. Actually, I'm not claiming I know the answer, because the processors change. So yeah, but why, the other day when Bharadwaj asked about the word also, if you see Hennessy and Patterson's book does use the word to mean only 32-bit. They don't mean it to be 64-bit. But when you actually work on the 64-bit processors, I find many times they align the word to be 64 bits, right? So I would like you to do these experiments and come with answers in the next class, right? Then it's a lot more fun, because it gives a very clear understanding to all of us how padding is happening. Where is it happening? How much is it happening? So what is it aligning it to? Okay.
Okay, ma'am.
Because it is a good thing. I mean, the answers are not wrong. It does padding to word boundary. Very true. But, it also does very interesting stuff. Of course, despite the fact that we do a very dumb structure definition, the compiler will be very smart. Okay. So you can think of it like that also. So that is, alignment, however, as defined by Hennessy and Patterson. Now I'm very, very, very specific. Please note that, because I know that in the videos, right, because it is talking about MIPS architecture specifically, it talks about a 4-byte alignment. Agreed? Am I right? If people have seen it, seen the videos. Whereas Hennessy and Patterson define alignment as address mod size of the operand. Okay. So if you have char, any byte, any byte address, any address in fact, is aligned. If you are trying to access a character variable, any address is aligned because it is a mod 1 equal to 0, right? So therefore, any byte can be addressed. That is an aligned address for the character variable. Now, if you talk about a short variable, 2-byte variable, A mod 2 should be equal to 0. So every even address is aligned, but not the other addresses. If you are talking about a 4-byte variable, A mod 4 equal to 0, which is what we are familiar with, right? So that is the thing. Okay, so the alignment, therefore, as defined in the textbook is A mod S equal to 0, where A is the address and S is the size of the variable. Some processors use only word alignment. Okay, they may not use this sort of alignment, they may use only word alignment. Some processors may use only word addressing, which means that you cannot actually put an address on the links, on the address lines, which is any arbitrary byte. It can only be a word boundary address. Okay, so if you look at the book in Appendix A, they clearly write MIPS is a byte addressable processor. And in fact, they have also made the statement that most modern processors are byte addressable processors, because otherwise, the performance can be very poor. Therefore, they became, earlier they were not, but now they are byte addressable. Alignment is A mod S equal to 0 alignment that is used. Okay, MIPS may use a different alignment, but this is the general alignment which is used. So I hope that is clear. Any questions on that? The other question that comes up is, how many, what should I say, what addressing modes do you have? So how do you address variables in memory locations, right? How do you access, what is the address? How do you get the address of the memory location that you are trying to access? That is the question. How do you get the address of the memory location that you are trying to access? So, the operations are now happening on certain operands. So what are these operand locations? This is the question that addressing modes actually address. So you have a register operation in which the operands are not in memory, they are in the registers, and the register information is given to you. Okay, so it's something like, I should have copied that from the book maybe, but anyway, I haven't made very strong slides for this part of the course. I should probably do, but trying to think of doing better slides for Appendix B. Okay. So there are, if you look at the book, there are some 7 or 9 modes that they talk about. Okay, register is one, right? Have you studied addressing modes in your COA, by the way? You must have, right? So can you people tell me what are the modes that you are able to remember now? I think some part was covered even in the videos. So
Memory direct addressing, memory indirect.
okay, what is direct addressing?
Like
Direct addressing only fetch the operands directly from memory into register. So
No, we fetch all the times when we address a memory location, we do fetch from memory to register. So the difference will be in how do you get the address of the memory location. So in direct addressing, how do you get the address of the memory location? Okay, this is correct answer Yagnahan has given. Address field of the instruction contains the effective address of the operand. Okay, so Bansi has given another of the addressing modes, which is auto increment decrement addressing. Okay, so first thing is direct addressing means you actually give the address directly, right? Like you say location 1000, location 10,000. Okay, there is nothing further for you to do. So what do? You basically go and fetch the memory location in that position, right? The value is given to you of the memory address. That is direct addressing. What about indirect addressing?
The location in
Because
the
there are
memory points
many.
to another memory location.
Yeah, so the thing is there are two indirects. There is a
Memory
registered
indirect.
indirect and a memory
Memory
indirect.
indirect.
So which one are you talking about?
Memory indirect addressing.
Address field of the instruction specifies the address of the memory location that contains the effective address of the operand, which is basically like your pointer. Do you agree?
Yes, ma'am.
Yes.
Basically, you're saying I have a pointer variable. Okay. So you go to the location of the pointer variable, and the pointer variable value will give you the address of the actual variable. Okay. That is basically the memory indirect addressing.
Yes, ma'am.
Okay. Immediate addressing. What is immediate addressing?
The operand
value
is present in the
is
instruction itself.
instruction.
Okay. The operand is present in the instruction itself. Okay. This is one, right? Then there is something called displacement addressing. What is that?
Like we move to
The
the memory location and then increment that position by the offset.
Yeah.
which
So
is stored in
what can
the
you think of
register.
as use for that? Yeah, this I think Brahmani has given base offset and index offset addressing, which is essentially what is called as displacement addressing. Okay. Right? So register indirect is what? We have now discussed direct, memory indirect, we have discussed displacement, we have discussed immediate, we have yet to discuss auto increment decrement, but register direct indirect is what?
The operand
Register
consists of
direct.
register.
Yeah, tell me, Pranav.
The
Pranav,
operand
right?
consists of, yes.
Mm.
So the operand in the instruction consists of a register address, which again points to, and the register consists of the address from memory, main memory also.
Okay. So the contents of the register are basically a memory location. Agreed?
Yes.
In register indirect, basically the contents of the memory location is an address of the memory, and memory of that location is fetched. So that is register indirect. In register, of course, both operands are directly in the register, so we don't have to talk to the memory at all. Right? Auto increment and decrement. We basically increment the contents of the second register, or what is called the offset register, by the displacement value, some fixed value, right? Size of an element, which is again like it's essentially combining two things of the array, right? We do the operations And then we also move to the next element of the array in one particular addressing mode. If you remove that, you will have two instructions that you have to do. First one will do the addition, second one will do the displacement. Okay, so they sort of decrease the number of instructions by combining multiple operations into a single instruction. Then you have what is called a scaled. This is also used to increment, the auto increment and decrement, the book says it is essentially used to do stack operations of push and pop, okay, and scaled operations to do indexing into the array, okay. So these are the addressing modes, which are, possible addressing modes, most popular addressing modes that are available, okay. So any questions on this? So, how does all this matter to the, computer architect? What matters is, when they started looking at these things, they said, okay, how many addressing modes do we really need? And can we do away with having so many addressing modes? Can we have something called a minimal set of addressing modes with which we can do most of the operations? So interestingly, MIPS processor decided to have only 3 addressing modes. What are they? They are immediate, okay, displacement and register indirect. That's all, only 3, okay. And they are able to achieve all the other things using those 3. In fact, they get even register indirect, if I'm not wrong, by just using displacement, sort of a thing. But anyway, they have minimized the number of addressing modes to just 3 of them. Why does it matter? We will see. Because how does it matter? It matters because when we go into the instruction, how it is encoded, then this matters actually. And, we'll look at that. But before we go further, what are the sizes and types of operands that we need to deal with? See, some old architectures used to have even string data types. Okay, and they had instructions which compared strings and things like that. Obviously, nowadays nobody is doing that. What do we have? What are the standard things that we have? We know them, right? C is a classic example of what all it specifies, the types and sizes of operands. Okay. Operations in the instruction set, you have the standard arithmetic and logical operations which are in the ALU, right? The data transfer operations, which are basically the load store operations that transfer data back and forth from the memory. Then you have control operations such as branching or jump. So what is the difference between branch and jump? Branch is conditional, jump is unconditional, right? So, when we are talking about ALU operations, that is where your addressing modes come into picture. Are you doing your operations only on registers? How are you fetching the memory? Is your operand immediate operand, or is it indirect operand, and so on. So there you need to therefore combine the opcode, which will talk about the operation, as well as the addressing mode. Okay, so the operation and addressing mode, if you can combine and have a few bits only for the opcode, then you are actually reducing the number of bits needed for the opcode. How does this help? It allows you to then have more space to handle operands themselves and other fields, right? So these fields can be, you properly specified, like the large constants that, the video talks about cannot be accommodated in MIPS, right? The MIPS gives you 16 bits for the um, 16 bits for the immediate value. Okay.
Yes.
So if it's, yeah, I'll be stopping after this. So if if you need an operand which is more than 16 bits long as an immediate operand, then you have to go for a very different encoding to get that value. So that is why he talks about how do you encode large operands. That is the sort of thinking that you need to do to define how your instructions are, right? So that's basically, the thing. So now when you talk about control operations like branching and jump, how do you specify the target address? Okay, where do you go if the branch is successful? So that also is done with what is called as PC relative addressing. That is, with respect to PC, we add the offset to get to the actual address location. Okay, so this is PC relative addressing. We'll stop here, come back around 12:30, around 10-12 minutes break, and take around further half an hour of discussion. Fine?
Okay.
Any questions in the
Okay.
whatever we have done for the couple of minutes that we have? Yeah? Somebody was saying something like that.
Ma'am?
Mm.
Yes, ma'am. Ma'am, what exactly, ma'am, why exactly is register so fast, ma'am? Is it because of like quality of the silicon which they're made in, or is it because of their extremely small size? So the search space of like retrieving something from register is fast. Why are they so fast?
Okay, I think need to ask an electronics person about that. If Rukma can answer, she can. Otherwise, I'll find the answer and let you know.